Hello, 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 hello. Okay. Yeah, so the next lecture will going to be started. So please go back to your seat and yeah, suspend your discussion. So yeah, welcome to our Research Aware Machine Learning Summer School. So the next lecture is given by Andres Gomez. He received a dual degree in electronic engineering and computer engineering from the University de Los Andes, Colombia, and a master degree from the Alari Institute, Switzerland, and a PhD from ETH Zurich, Switzerland. So he has over 10 years of experience with embedded systems, and he has worked in multiple research labs in Colombia, Italy, and Switzerland. More recently, he has worked as an R&D engineer at Miro Miko AG. He has co-authored over 30 scientific articles and has contributed to multiple open source projects. He's recently a research fellow. He's currently a research fellow at the University of St. Gallen, Switzerland, and his current research interests include batteryless system design and Internet of Things and the Web of Things. So today he will talk about the zero power machine learning. So Andres, now the stage is yours.
I'd like to begin with a question. Did any of you ever own one of these? Maybe with a show of hands. I used to have one back when I was in my undergraduate studies. And this is the Nokia 1110. It came out in 2004. And to this day, it remains the best-selling phone of all time. Now, I remember that one of the things that I liked about it is that I could use it for several days and it would not run out of battery. And this was impressive, given that it had a battery of only 850 milliamp hours. Now, your current cell phone probably looks something like this. This is the iPhone 14 Pro Max that came out just a few days ago that you still cannot buy. But I can assure you that when you are able to buy it, you will probably not be able to use it one full day if you're using all of the features that it has. And this is the case, even though the battery is significantly larger, right? The battery is more than 4,000 milliamp hours. So this big trend of functionality increasing and also increasing the cost, the size of the battery, the environmental impact of manufacturing these ever powerful devices is something that I like to work to avoid in other domains. In particular, I work in the field of the Internet of Things, where we look at, or we try to make environments and devices smarter at different levels. It could be from the quantified self, right? So having wearable sensors that help us get insights into our daily lives. It could be with smart homes and trying to minimize the energy consumption, or it could be at the level of cities where we try to optimize our energy use and perhaps also our comfort in cities. And we do this for good reason. We spend a lot of time indoors, right, in houses and in buildings. They consume a lot of energy, and if we want to be more mindful of how we use our resources, for example, for things like lighting and heating or cooling, it's important to be able to get lots of data so we can make better and better decisions. So how can we improve? If you look at current sensing devices, they look something like this. In general, it's one big battery with a little bit of silicon on top. Right? In certain scenarios, especially when you need some more special batteries, they might be 90% of the volume of the whole device, which is something you'd want to avoid, right? Because we have to ship these around. And the batteries are expensive. In certain cases, they could be maybe 50% of the cost of the actual sensing device. So my research tries to develop novel design paradigms that try to make sensing devices, these ultra-low power devices, much more cost-effective by using lower cost components compared to batteries. Hopefully, we can even use organic components, for example, organic solar cells. We can hopefully make these sensing devices maintenance-free by tapping into environmental energy sources such that they have much longer lifetimes compared to something that has all of the energy we'll get when it's being deployed in a battery. And then we make them more environmentally friendly overall, right? In the way we manufacture these and in the way that these operate relatively maintenance-free for hopefully long periods of time. So this is roughly what I do. Let me now tell you a little bit more about myself. So my name is Andres Gomez. I'm very happy to be here. So thank you for the organizers for inviting me. It's very lovely to tell you a little bit more about my research. Maybe if I can get just by a show of hands, who is a computer scientist and who studied informatics? Okay, and did anyone study electrical engineering or electronics engineering? A few people, some less. Is there any other degree, any other physics? Some physics? Okay, anything else that I'm missing? I can hear. Mathematics, okay, cool. So I am originally from New York City, born and raised. But as you can tell from my name, my heritage is from abroad. So my parents are Colombian. I'm also identified Colombian. But I've been living in Switzerland for many years now, over a decade at this point. And as it was mentioned in the introduction, I did finish my PhD in ETH Zurich on a topic called batteryless sensing systems. So I will tell you a little bit about some of the research that was done during my PhD and that has grown and extended through my time in industry while I worked at Minomiko, and then also currently some of the stuff that I do at the University of St. Gallen. So please don't be shy, ask me questions. We have plenty of time. I will talk a little bit about hardware. So if there's something that you don't understand, just please raise your hand and I can go into a little bit more detail. So let me first start with a general overview of how we as designers envision our sensing systems. We have this traditional device lifecycle, right? So we have, let's say, this timeline, and then after we design and manufacture devices, we deploy them in the end environment, right? At this point, it's like a baby is born, right? It takes a lot of effort to make sure that everything is set and that it's working the way we expected it. And after this initial deployment phase, it enters into the more mature, steady production state where it's doing its thing without any hitches, assuming you developed everything correctly. So ideally, we kind of, as designers, want to just stop time and make sure that it stays in that state, and we don't want anything else to happen. But devices, just like humans, they age as well, right? So their performance decreases for multiple reasons. There are some weak points within the hardware devices that we design. And at some point, eventually, they will also die, right? They will need to be replaced because their components are no longer functional. And we need to get a new set of components so they can continue to do their thing. When we analyze the things that might degrade and might stop working, you can look at the mean time to failure for several of these components. And if you look at the silicon, if you look at the data sheet, sometimes in the data sheets, they have these informations. And they say that if you keep the right temperature, if you keep the right voltage, if you protect it from radiation, et cetera, your silicon could last for millennia, right? Of course, those are very strong conditions. And of course, they don't test it for thousands of years. They do some special aging tests where they extrapolate that under normal conditions, it would take thousands of years. But okay, so the silicon, we can assume, will last for decades if we take care of it properly. If you look at things like a solar panel, it depends a lot, particularly if it's outdoors or if it's indoors. If it's outdoors, you can imagine it's exposed to the elements, rain, sleet, snow, depending on, or heat, depending on where you are. And this can affect, of course, the lifetime of the device. If it's indoors, it looks a little bit better, but you still have to take care of it. You still have to control temperature, and it could last theoretically some decades, according to testing from the manufacturers. When you get to the batteries, however, this is typically one of the bigger points of weakness. Most battery chemistries have this, let's say, this characteristic that after charging and discharging them for many cycles, they lose their capacity. So they store less and less energy after each successive cycle. And at a certain point, after hundreds or thousands of cycles, depending on the chemistry and the specifics of the battery, they will basically have very little charge left. Maybe you know this yourself from laptops, the old laptops that you have already charged and recharged many times. They will last a few minutes, right, after several years. So this is one of the big weaknesses that we want to address by even asking the philosophical question of, can we develop electronic devices that work without big energy storage systems, right? So taking away this assumption of very stable power supplies. And then a very closely related question is designing things to maximize this lifetime the only desirable goal? Do we want them to be just like humans, that we just want to extend our lifetimes as much as possible, or is there another alternative? So I believe that there is, right? And for this, I would just like to explain the two different goals that you might have: predictability versus resilience. So the first one, when you have the mindset of predictability, you want to design a system that will live as long as possible, right? That will have the longest maturity stage in its deployment. And so for this, you need a large energy cycle. I will use the variable Q as to define an energy cycle, basically how much energy the device can store. And so when you have this mentality of predictability, you want the empty and the full states to be as far away as possible. You want to have as big a battery as you can afford. And then it will be initially charged. And then with time, very little, you can predict how much you will consume. And then you will extrapolate a lifetime. And hopefully this will be a big number. And then you can sell your device saying, look, with this battery, it will last 5 years or 2 years or however many years, hopefully a larger number. So the issue with this is that it's nice to have a long discharge curve, but then that also means that you have a very long way to charge things up again. And in certain cases, particularly when you're dealing with energy harvesting, this is not desirable. So the alternative perspective for me is to think a little bit about resilience. And so instead of having things that live as long as possible, I want to design things that will revive as quickly as possible. And so to do this, instead of putting, a large energy cycle, I will just have a very small energy cycle with a small Q. And so in this scenario, empty and full states will be very close together. And yes, they will discharge quickly, but they will also recharge quickly, which is something that is a positive thing for what we will be looking at in the next few systems, right? So to summarize, the first approach is to have a predictable design time, a predictable lifetime of design time. And this correlates more or less to what we expect from a normal human life. We want to live it as long as possible. But this other approach is more like of a resilient life. And it's almost like having zombies, right, that are dead, but they can revive at any moment as soon as they're a little bit of energy. And so this is more or less the mindset that we will have. Now, let me say a few words about energy storage, since we will be talking a little bit about it and also about batteryless. So there are many different ways of storing electrical energy, even at small scales, of course, or large scale as well. There are many different options. But when we look at small electronic storage, there are usually many trade-offs. I've mentioned recharge cycles. There's also the power and the energy density and things like leakage. So if they self-discharge just because they cannot hold the energy together. So one way in which these can be viewed separately is something called a Ragone plot. And the Ragone plot just has these two axes. So here in the x-axis, you have here power density. And then in the y-axis, you have the energy density. So let's look here first at the case of batteries. This has a high energy density, but a very low power density. Can anyone venture a guess as to what that means, like in practical terms? What does having a high energy density mean? So it means that you can store a lot of energy in a battery, right? Typically for a small battery, you can store maybe thousands of joules. But the small power density means that you cannot discharge it or charge it very quickly, right? You're limited in how much you can extract or how much you can put in, right? So the opposite from batteries are things like film caps or sometimes even ceramic capacitors. These are things that have very low energy density, meaning that they cannot store large amounts of energy relative to their size, to their weight, but they can charge and discharge very quickly, which is useful in certain scenarios where you need a lot of energy in a very short amount of time. Then it's a very good idea to have a capacitor because it can support this, right? There are many other technologies. I won't go into them. Also, I'm not a battery expert. I'm a batteryless expert. So in general, what I want for my type of systems are things that have this high power density and have high recharge cycles, right? Because I'll be charging them and discharging them many times over the period of a long, hopefully, deployment of many, many, many years. So for the most part, I try to use ceramic capacitors whenever it's possible. Ceramic capacitors do have these two properties. They do have the restriction that because of the low energy density, you cannot store large amounts of energy. So when the application requires some sort of peripheral or some sort of device that requires a bigger chunk of energy at one time, then we have to use something else. So overall, these my research can be summarized under the term energy-driven design. Within energy-driven design, you have these three, let's say, blocks, right? So the first one on the left is a sporadic source. This is in contrast to a battery, which is a stable source, right? It always has energy available and you can extract whenever you need. So a sporadic source, in contrast, is something that offers energy only part of the time. And it's usually then a combination of the primary energy from the environment. This could be light, both natural and artificial. It could be temperature, it could be movement, kinetic energy, right? There are many different possibilities. Then you have to have a transducer, right? Something that will convert that primary energy into electrical energy. And then you need some sort of buffer. Even in a batteryless system, you need some sort of energy buffer to condition the system and to be able to make some small guarantees. And I'll get into this a little bit later. So this sporadic source will supply energy to an application circuit, right? An application circuit in the case of low power sensors, they usually have these three components. They have a sensor. It could be something as simple as a temperature and humidity sensor. It could be a camera, a microphone. There are many other sensors. Then you need also a microcontroller. Typically, it could be an ARM or a RISC-V microcontroller to read the sensor, perhaps do some local processing, and prepare the data for wireless transmission. So for this, you also need a radio. And there are many different types of radio. You have short-range protocols like Bluetooth. You have long-range protocols as well. And at the end, so once this application circuit has gathered your data, processed your data, and transmitted your data, you need some sort of receiver and infrastructure where you can handle all of this data. And it could be something as simple as your cell phone that receives Bluetooth data, or it could be big cloud infrastructure, right? So compared to traditional battery-based design, when you design these energy-driven systems, they aim to have a less expensive energy source. And then we have an application circuit that will not be powered on continuously. When there's no energy, the system will consume zero power. In fact, that's kind of why I've chosen the name for this. I don't usually, there are many terms for these types of systems. Here, I wanted to say zero power because there will be a point in time, and it's almost like the default state where they will consume zero power. And there's nothing more efficient than something that does not consume any energy. So I've decided to split my talk in these 4 topics. I'll try to spend maybe 10, 15 minutes on each of one. I can try to adjust, and so in case you have more questions, we can shorten some of the other topics as well. I'll talk then about the sporadic energy source. I'll go into application circuits. I will talk about some machine learning models that we've been able to execute on these ultra-low power devices. And then I'll talk a little bit about wireless communication at the end. Are there any questions so far? Okay, So I'll be talking, so the first section is a little bit more hardware oriented. So for those of you who are not electronics engineers, just please don't be afraid to ask. So the first thing that you need to know about energy harvesting is the great power imbalance. If I draw an axis of power, this is logarithmic. So we go from microwatts all the way to 1 watt. And if I put together the transducers, so the things that generate electrical energy, and I order them by their power density, so normalizing by their area, I get something like this. The best case scenario on average, so there are sometimes niche cases, but on average, the transducer that offers the most energy is the photovoltaic cell. And in normal conditions, it can offer maybe up to 10 milliwatts per squared centimeter, right? But again, this is the absolute maximum in the best case scenario. When it's dark, of course, it gives 0. And then the average is somewhere in the middle, depending a lot on the environment where you're deploying your device. When you look at the consumption, the energy consumption, so your devices, your application circuit, it depends quite a bit. It has a wide range. It can go from average of a few milliwatts to hundreds of milliwatts, depending on the components that you use, whether you're using some type of special type of camera, or if you're saving data to flash memory. Flash consumes a lot of, something like an SD card consumes a lot of power. You might have multiple CPUs. You might have some special radio that you want to have a very long range link. So these generally consume, when they're active, they can consume easily hundreds of milliwatts. The good thing is that most modern low power electronics have some sort of sleep state where I can turn things off efficiently. And for the most part, you can get it down to maybe a few microwatts. So basically what we want to do is we want to have some sort of balance by leveraging this sleep state such that there is balance between the energy being generated by my transducer and the energy that is being consumed by my application. So the easiest analogy of this is that energy is like money, right? It's very difficult to produce, but it's very easy to spend, right? And we have to get over this fundamental limitation. So when we're trying to understand environmental energy, the best case, and I mean, it depends so much on where you are and the environment, the best thing is to try to do in situ measurements, meaning at the actual location where you will deploy your devices. Doing this can sometimes be quite challenging. Here, some colleagues of mine, Lucas and Moritz, we're trying to find out how much energy we can get from thermoelectrical generators that are tied to the wrist. These TEGs produce energy as a function of the temperature difference between my body temperature on the inside and the external environmental temperature on the outside. And you can imagine if we want to get good measurements, we have to walk around both inside and outside, right? In different days, at different times, in different environments. And to do this properly, to measure these devices properly, we needed to have a very cumbersome lab setup. We had a car battery, an AC inverter. We had 2 very robust desktop power measurement units, so we can record how much energy was being generated as Moritz was walking around the city of Zurich. So this is not scalable, right? You cannot do this for prolonged periods of time on very different environments. So to address this, Lucas and I got our hands dirty, and we decided to implement something that would facilitate this task. And so for this, we designed the Rocket Logger. It's a small device. It's also something that I will have here that I'll show you a little demo at the end. And it's something that has exactly what we need for energy harvesting. It has 2 current channels. This will allow us to generate how much energy or how much current we're generating from the transducer and how much we're consuming from the application circuit. It has voltage channels as well, so we can measure different things from different components. We also have digital channels to facilitate the post-processing and really being able to determine what energy is being consumed by what. This is an open source project. You can download the hardware design, you can download the software, you can make your own versions. It's being used by people all over the world. And you're more than welcome to try it out as well. And I can show it show you how it works later today. So let me show you what we were able to do with the rocket logger. We wanted to answer the question, how much energy is available indoors in our offices at ETH, And to do this, then we created this small little PCB towards the right of the rocket logger. And it has a small solar cell, it has some other circuitry. And with this, what we're able to do is gather a data set of 2.5 years, I believe, and with 6 different stations in our office building. And we were able to measure how much energy this small 15 square centimeter solar panel will generate. So I'll show you just a few of the sample measurements. You can, of course, download. Here's a link. You'll have the slides. You'll be able to also download and look how much energy was generated in these different locations. So here I'll just show you a few. This is the office building at ETZ. This is where my office was located. And here I've just selected a few specific points, right? So these 4 points, and I've plotted the daily average energy for over 2.5 years. And the violin plot just shows the distribution of this average daily energy over the 2 years. So to give you an example, location D had the biggest variability of them all. And this is because, as you can see here, it's very close to a window and it's facing east. So in the summer months, it has direct sunlight for multiple hours a day. And in the very best day over these 2 years, we were able to harvest almost 79 joules of energy. Maybe you don't have an intuition of how much that is. You will before the end of this talk. It's a lot of energy, right? You can do a lot with low power sensors that have 80 joules of energy per day, right? But I will also highlight that the other nodes that did not have that much natural light and were based mostly from artificial indoor lighting, they received significantly less energy, right? So point A, for example, which was where my office was located, in the best case scenario, gave maybe 2.5 joules, right? So the key message in this is that even the same hardware, right, same solar panel in the same floor of the same building, just by the fact of being deployed in different offices, there were roughly offices, okay, maybe slightly different sizes, but they were the same things with windows. But because of the many variables, geographic, astrological, right, of the path of the sun, et cetera, the amount of energy that you will be able to harvest varies significantly, right? So how can we make use of this energy, right, in a useful way? So the idea behind these zero power batteryless systems is that they're most useful, they're best suited for the job when you have this one coincidence, or sorry, not coincidence, when you have this, I'm sorry, when you have this alignment between the information that you're interested in and the primary energy. When you have this alignment, it's a very good idea to think about one of these zero power batteryless devices. And this works it is a very nice concept because when you do have this primary energy, then you can generate the electrical energy that you need to gather the information about the phenomenon that's generating the primary energy. There are multiple examples of this, not that many, unfortunately, believe me, I thought about it for many years. The 2 easiest examples for this is something like a batteryless camera. A batteryless camera is something that can use light to generate electricity, to generate energy, so that it can take pictures in the visible light spectrum. This makes a lot of sense because if it's dark, okay, it doesn't harvest any energy. It doesn't matter because a dark picture contains no information, right? Another example is with movement. You can harvest energy from movement with something like a piezoelectric device, and you can use that energy to gather information about the movement that generated that primary energy, right? There might be some small delays here, right, between when the energy is first available, but we try to minimize this response time. So the way we try to adjust for the variability, not just in the energy, right? Because that was for one single transducer. We also have to take into account that there may be many different transducers, right? There are many, many companies that manufacture different types of solar cells, and that's just solar cells. We can have also AC sources, like the piezoelectric thing that I mentioned, PGs. There's a DC source, but it has very different characteristics. So to be able to use virtually any type of transducer and not have to worry about your application, my colleagues and I, we proposed this thing called the energy management unit. The main purpose of this energy management unit is to decouple the transducer from the application. And this means that I can harvest energy within so this subsystem is independent. It can be optimized locally to maximize the input energy. And then I can also minimize the energy being consumed by the application, which requires a different voltage, a different operating point. So when we have this decoupling, we can perform this simultaneous optimization so that we maximize our input and minimize our output, which is the best approach, right? So with the EMU, and by this decoupling, we're able to have scenarios like this, that you can have a small transducer that generates only 5 microwatts of input power. Let's say it's a low number, but it's very easy to see those numbers in transducers. And we can still have an application that can consume, when active, 100 milliwatts, right? Now you might be thinking, wait, how 5 micro and 100 milli, it sounds like there's some energy disbalance. But the key thing is that I said when active, right? So remember, we have these two states, sleep. There are normally many states, but it can get simple. It can be reduced to just a sleep state and an active state. So the way the EMU works is that when it's fully discharged, then the device is simply off, right? It consumes 0 power. Once you surpass a certain threshold and you can accumulate energy efficiently, then the device enters sleep mode, and it slowly trickle charges a small capacitor such that at some point it reaches a threshold when I have enough energy to turn on and run one task on my application. So at that point, and at that point only, based on that signal, my application circuit can wake up, perform its thing. As you might remember, the capacitors have very high power density, so I can have this huge peak of energy. They can handle it with no problem. And then you will have your task execute reliably, right? I'll just point out then the energy that you can consume should be, it depends. So this is some hardware details about regulators and things like this. But I'll just like to point out then that the energy that you're consuming is the thing that's available. So electrostatic charge that is accumulated in your capacitor between these two different voltage bands. Right? That's a technical term. Just thought it was important for the electronic engineers. The rest, please don't get confused. The only thing you need to know is that there will be also some offset, which is very clearly stated here. There is some small amount of energy that went into raising the voltage of the capacitor that I cannot use. And this is also proportional to the capacitance, right? So which is related to the storage capacity, right? So this goes back to the argument that I was mentioning earlier, that it's better to have a very small energy cycle Q such that this offset is as small as possible, but I can still have a large enough delta between the two different thresholds that I can still power my application with high power for a limited amount of time, right? This is sort of like the summary of how the energy management unit works. And it's quite reliable because you can have infinite ways of charging it up, right? It can be very small, it can raise, right? The only thing that it changes is that the speed at which you charge up the capacitor changes. And this is what absorbs the variability in the instantaneous input power. And it has no effect on the reliable execution of the application. So just to relate how this has been used or can be used, this general perspective of opportunistic execution. Imagine you have one of these batteryless cameras in your room, and the input power inside this room is highly variable, right? So let's say it looks something like this. Someone came in for 15 minutes, let's say there was some variability in the input power, maybe from the natural sources. Then after 15 minutes, let's say the lights were shut down, so the input power goes almost down to 0. Then a few minutes later, someone else comes in, turns on the lights, you have power again, and so on. This is like a 1-hour trace, which was taken from the data set that I mentioned a few slides back. So for the batteryless camera, and for one of the systems that I will show you later on, assuming we have time, this power trace will result in a behavior as follows, as you see there. It will take maybe 15 minutes for the batteryless camera to charge up and to be able to have enough energy to take a picture. Then it might shut off. It doesn't matter. It will have non-volatile memory. Then once it charges up again, it can load the picture that was taken a few minutes earlier, start processing it, process it little by little in these small steps. And then at the end, before the hour is up, it was able to harvest enough energy to finish processing and transmit the result of the image processing towards the central server. Right, this is just one example that brings together the different things that I'm mentioning. And I will also show you a little bit about this system of this batteryless camera later on. So to wrap up the energy harvesting part of the talk, this type of operation that I just mentioned in the previous slide is also sometimes called intermittent operation, because the devices at some point during the execution might turn off and they need to save their state. So when you have these applications that will run on some hardware that might not have a reliable energy source, you need to handle, it should be intuitive that you need to handle it a little bit differently than you would with a battery. So with regards to the sensors, many, especially the simpler sensors, can self-calibrate. So it's fairly easy to just shut them off for as long as you want, and then you turn them on and you have a relatively good measurement very quickly. Certain other sensors, particularly chemical ones, are very different. They behave, they change their sensitivity if you operate them a little bit randomly. Let's say if you shut them off at certain times. It also depends on the environment. It's a whole different story. And we have worked with some colleagues at TU Graz on this topic. So you're welcome to read those papers if you're interested in how to compensate chemical sensors that are intermittently powered. If you then just look at the processing is relatively simpler, right? A processor is just this little thing. Normally you can stop it whenever you want, right? And then you can save your state, you can have some sort of checkpoint. And when you have energy, you can just restore the data, continue processing. This is relatively easy. There are lots of work. This is the most popular topic to publish about over the past 5 years in the batteryless or the energy harvesting intermittent community. But yes, so this is a fairly well studied problem of how to stop processing efficiently without too many overheads. Then more recently, let's say the new frontier, I would say, of this domain of intermittent operation is to be able to work with wireless transceivers in an efficient manner. Now with wireless communication, it depends a little bit on the protocols that you have. If you have an asynchronous protocol, then it's fairly simple to stop because by definition, it's asynchronous. So you choose when you want to start or when you want to stop. So this one is almost trivial. But when you have synchronous communication, and there are many scenarios where you would want to have synchronous communication because you have more data, you get more throughput, then it's hard. And this is, let's say, some of the more trickier problems. And I'll talk a little bit about this at the last part of the talk. So are there any questions? We're roughly, yes, please.
So I'm thinking about not like a city, but for example, So I repeat my question for the online audience. So I have a question related to the scalability of the proposed approach. So you're talking about you want to collect energy for giving energy to a camera, but I'm thinking about this could be scalable, so just to provide energy to all the devices that you might have at home. For example, you could also have information about how many power usage you have throughout the day in average. So you know that, for example, when people are at home, you're going to consume more energy, while, for example, when they're out of the home at work, then the house could collect more energy, and all the devices could be that are not sensible. Like, for example, the fridge should be always on, while other devices could also be switched off. So I'm also thinking about, actually I'm wondering, which is actually the hardware technology able also to collect the amount of energy also for a whole house, or does the hardware only support minimal amount of energy just for one camera or something?
Okay, so your question about scalability was really a bigger scale, right? So the answer is it does scale, right? So, but this is a totally different field, right?
Okay.
And so you of course have people who for decades have been studying this problem of, say, microgrids, or of having solar panels on your rooftop, right? And there are certain areas that are, that can use this more effectively than others. Spain gets more sunshine than Northern Europe, for example. So there it would make most sense, for example. And it's difficult as well, right? Because as I mentioned, the thing about energy is much more difficult to produce than to consume holds at any level, right? So something like a washing machine or a water boiler consume significant amounts of energy that you need a relatively large solar panel or a large amount of energy to be able to power these things. So I hope that answers your question, right? So
yeah, it does. Thank you very much.
Okay, so I'm gonna speed things up for the rest. I wanted to slow down for the beginning. So, and I might skip some slides later on. So the first thing that the simplest application that you might think of for these type of harvesting-based systems is something like Ble Beacon, right? So this is the platform. It's actually the one that I have here for the demo later on. And when you perform a power measurement, right, it looks something like this. This was actually a measurement taken with the rocket logger. And here I was in low power mode in the beginning, and then there's a trigger, let's say a button press or something like this. The device then wakes up. There's a small operating system behind. It has to configure certain things. It has to configure the radio, transmit constant data, and then shut down, right? This is the simplest possible application that you can think of. When you do thousands of measurements and calculate the energy consumed by this simple task, you have a probability density function that looks something like this. It's a very narrow peak around 108.2 microjoules, right? So this means that it's a very constant energy, right? There's very little variability, right? When you look at the cumulative density function, it's basically a step function, right? So this means that if your energy storage can only store 100 microjoules, you have a problem, because all of your tasks will consume more than this, right? But then the question is, what is the minimum energy storage size that you should have for this application, right? And then my answer is to look at the point where the cumulative density function reaches 1. And this is what I call the batteryless limit, because at that point, that is the minimum amount of energy storage that you need, such that you can cover the execution of your task, right? Taking into account any possible variability, right? So if I round up here, and if I have a device that can store 109 microjoules of energy, then I know that I have reliable execution, right? Because it doesn't depend on the input trace anymore. And I'll also have this minimum startup time, meaning that my device will wake up as fast as possible, maintaining this characteristic of reliable execution. Now, just to tie the numbers here from this particular platform with the numbers that I showed you in the previous section. So these 109 microjoules per activation means that you can have almost 30,000 activations per day, which means that during the daylight hours, right? Because again, you're only on when there's daylight. So you can have roughly 3 packets per second. I should have mentioned the small detail that in this, in this one activation, these 3 peaks means that you have 3 packet transmissions. This is traditionally done because in Bluetooth you have 3 advertisement channels. So at one point you want to advertise on those 3 channels, right? So you have 1 activation per second during the daylight hours. Right? So then with this initial prototype that was developed during my PhD, I then went into industry and refined it a little bit further. And we designed something called then the meter card. And the meter card has the same concept that I've been mentioning a couple of times already. It's something that without light, it does nothing. It consumes 0 power. It cannot gather any data. It cannot process any data. It cannot transmit any data. And only when I, as a user, decide to, for example, take it out of my pocket and expose the solar cell to light, only at that point does it actually turn on. And it usually depends a bit on the amount of light. But it can turn on within a few seconds and then start gathering data, processing data, and transmitting data. Right? So with this small card, in fact, actually, I can pass it around if you wish. Maybe you can pass it around so you can see the hardware design. It's a sensing device that gives the user some agency that only when I know that I expose it to light, only then will actually work. But then it's also an active system, right? That has, let's say, a radio, it has sensors, it has the capacity to process some interesting amounts of data and also perform active wireless communication. So this is also an open source project. You're more than welcome to take a look at it. The website is metocard.swiss. You can download the hardware design, the software, make it your own, and do what you wish with it. Right? So this was well accepted by the community. It has won a nice tech transfer award from High Peak. So now we finally get into the ML part. I spent 40 minutes on the 0 power part. Now I'm finally going to show you some machine learning on it. Now, hopefully by this time, you can understand that I'm talking to you about systems that are very low power, right? And very constrained. So they have, compared to big systems and compared to perhaps some of the other talks that you've seen with big FPGAs and big cloud services, these are very limited microcontrollers. So accordingly, the machine learning models that I will show you are rather simple, right? Compared to some of the other things that you have heard over the rest of the week. And they're simple because we're really pushing this limit on minimizing the requirements, both from the hardware and from the energy perspective, the requirements to run these simple models. So as you see, it's a card. And once we had this meter card, we were thinking, okay, what can we do with it? Can we run some machine learning models, right? Or some classification models for different types of gestures, right? So for a gesture, and we do it with an accelerometer, right? So there's an accelerometer on the device. And so to classify gestures on an accelerometer, you need a series of data, right? And typically, depending on the gesture, right? It's not just the pose of the card. You need a larger amount of samples to do this, right? So compared to the previous slides where I've mentioned, right, just from the normal EMU operation, that as soon as you have energy, you can do things, that's no longer applicable for this type of application, for this gesture detection, or for any type of time window processing, because we're adding a new requirement, right? So when we're doing data streaming applications, we need to have a certain amount of data, right? Classifiers typically have this clearly defined window. In the case of the model that we have for this device, for this gesture application, we need 20 samples, each 20 XYZ samples, so 60 samples overall. We use a frequency of 10 hertz, so it takes 2 seconds to have enough data to perform one classification window, right? So let's say the finite state machine of this device is pretty much the same as before. with some minor tweaks. So if there's 0 energy for some time, the device will be fully off, right? 0 power, 0 energy. As soon as I expose it to light, right, then it enters this energy efficient sleep mode. But here, to gather accelerometer data, we also need to have the accelerometer on. Otherwise, it will not gather any amount of data. So now, before I can turn on my microcontroller to process the data, I need to make sure that I have not just enough energy, but also enough data so that I can perform the classification of the 60 samples. Now, this is an additional dependency, as I was mentioning, and it can lead to certain inefficiencies in certain cases, right? So the case where it leads to inefficiency is, let's say I'm in an environment that has a relatively good amount of energy. And so I charge up relatively quickly. And within a second, I already have enough energy, but I don't have enough data. So I have to wait. And so basically, I cannot harvest any more energy because I cannot put it anywhere, right? I cannot damage my device by overcharging it. I have to stop harvesting energy, and then I'm losing energy, right? And I'm losing energy for 1 second, the numbers that I mentioned, until I finally have enough data, I can perform my classification, and then I can charge up again my very small capacitor, right? So this are some energy losses, right? And this is, let's say, a fundamental limitation, right? So here we're trying to find out, is this EMU energy-driven behavior applicable to other devices, to other applications, such as this data streaming application? And the answer is yes, but it's not optimal in terms of energy efficiency, right? So, and this is the perfect counterexample to demonstrate this, right? So now let me talk then a little bit more about the gesture detection. I'm going to speed up because it's relatively simple for perhaps some of the experiences that you've had already. So we gathered some data set. We had just 2 different classifications. And we distributed the set with like 12 participants. We had, let's say, this data gathering campaign. And we also took into account different types of, let's say, different axes, right? So thank you. So if I have this card and I want to shake it sideways, we ensured that the participants moved it sideways on different axes, right? Same thing for the up and down, right? You can shake it up and down like this or like this, right? Upon any different axes. So we handled all of these different possibilities when we were gathering the data. And then we trained a relatively simple model that had a relatively high accuracy. Here, I'm going to go quickly. This is fairly standard. We used the tool from a company called InfXL. And they have some web services that you can use where you can upload your data and you can perform some training as well. And then this has a very specific structure. It's not a convolutional neural network. It's called a light neural network. And it's very simple. It performs only additions. And it's relatively efficient in terms of energy. But of course, it's limited in its applicability. You can't run complex image processing on it because the computational power of the model is relatively simple, but it worked well enough for this type of classification. Right. So here, just to show you an example of what it means, here, this is me shaking it sideways. You can see this little oscillation on the y-axis. And then, so these 60 samples that you see here, right, they go into this InfXL data processing model. And then afterwards, you have a classification. And then this is what you can transmit, right? And so you're compressing, instead of having to send 60 raw samples, you can send basically 2 bits where you can have the classification, right? So when we do the measurement of how much energy it takes to run this classification model, you can see here, compared to the one that I showed you a few slides ago, now we have this relatively big section here when we're reading the sensor, performing the model, and then during these are the 3 peaks that you had seen before, right over here. This is the Bluetooth transmission. Instead of taking like 10 milliseconds, it takes roughly 40 seconds to perform the entire cycle. And in terms of energy, so before it was like 109, I believe. With this, it goes up to 700 and something microjoules. Now, the sleep state also changes because we're now gathering data continuously, right? Hoping that we will always be able to process the data, assuming we get the energy. And so the sleep state went from maybe 10 microwatts to 60 something microwatts because the accelerometer is always on. right? Now, I had mentioned all these, emphasized over and over again, the quick response times, the wake-up times, right? So here we had to adjust, and actually I don't think I wrote it, but you can imagine that the queue that we had before of 109 no longer works, right? So I have to use a slightly bigger capacitor. I forget the number, I think it was 200 microfarads. And then with this, it will be able to guarantee that we have this atomic execution, right? Now with this measurement, what I had done is I emptied everything. So I manually emptied the capacitor. So it had literally 0 energy. And I exposed it to 900 lux, which is a fairly generous amount of energy, amount of light, sorry. And in that case, it took roughly 10 seconds. This is the worst case response time, right, for that amount of light. And so within 10 seconds, right, it was charging up here, this capacitor, and then at some point here, you see the normal activation cycle. So each time this thing goes down, it had gathered 2 seconds of data, and it's able to perform the gesture classification. Right? Yeah, so that's one activation. Here I have just a demo. I guess I'll skip it. I'll just show you briefly this thing about this little video. Basically, we're now using the card and some gestures to control different devices with a small, very simple user interface. So if he was a student who wanted to see how these devices integrate, here I'll just show you really quickly that based on how you tilt it and how you, with some gestures, you can control the intensity of the light. You can also change the color. You can also move a robot. If you're interested, we can talk about this later. I'll move ahead in the interest of time. Are there any questions so far? Online, is there any question online? Or? No? Okay. All right, so the gesture detection, it was a relatively simple model, right? That has a low bandwidth, relatively low bandwidth sensor. I'll now show, you have a question?
There's a question in the chat from Oliver. Why a simple DL model and not some other model?
So in general, we want simple things because they consume less energy, right? In general, right? Then the question will be, is this the simplest possible model, or can we do more with this model? And I think the answer is yes to both of those questions, right? But now I'll talk briefly about another model. It's a little bit more complex, right? Okay, so I will go briefly through the batteryless camera. So one application that we implemented on this batteryless camera. And the application was to detect or to have an estimate of the number of people in a room. You can imagine this is a fairly generic application. So this is what it looked like. And here we actually wanted, for privacy reasons, to use a thermal camera because it's less easy to recognize people with a small thermal camera. So the tasks, high-level tasks, were just the same 3. So we take a picture, we process the image, and we transmit the result of the processing through Bluetooth. And of course, we have also this nice compression if we only send the processed results. So this is again, it's a fairly, we started this work several years ago. So this detection algorithm is relatively simple, but it works okay. So we do this with a small, we implemented this application with a small binary detector. Right? And the way these small binary detectors work is we take a small patch of the image and then we ask a binary question, is there a head in this small patch, yes or no? And then we continue scanning the image, so the next one, and then with a certain amount of stride, if you have multiple heads, you can get detections that look like this, right? You have multiple overlapping, if you have a small stride length, you can have multiple overlapping detections. Then you can use something called non-maximum suppression to collapse these overlapping detections into a single detection. And then after this, you can just count the number of resulting detections that you had. And this is then the occupancy estimation. But these type of processing, even for these relatively low resolution images, resulted in over 5,000 tasks being called, right? So it's a relatively big processing task. And we wanted to show that we can run these relatively complex applications even on a small zero-power batteryless device. Now, when we try to do this, we have different approaches, right? One approach that I mentioned before is to just do things atomically, do things at once. So here I'm only writing 3, but think of it as the 5,000 tasks. So I would just measure how much energy it takes to perform all those 5,000 tasks. I have my queue for that, and then it will work, right? Another approach is because we have this abstraction of a task, then I just run one at a time. And then for this, all I have to do is store enough energy for the maximum energy of the tasks, or the task that consumes the most energy. And that's it. I do have to store the data, intermediate data in non-volatile memory after each execution though, right? And then here, I hope you already have an intuition of the different overheads, right? So certain overheads will be related to the large energy storage size. Other overhead will be related to the cost of saving and restoring data in my non-volatile memory. So the first simple solution, even though it's simple, it has this large queue overhead. And then the second one, which is also simple and works fine in certain cases, and this one, because there's so many tasks and you have to save and restore a lot of data with a big image, this will result in a huge overhead. So how can we optimize these types of applications? It was a relatively, this was a relatively long project, and it involved going back and addressing even the programming model. So we used a very specific programming model that the programmer had, so it's like a dialect of C, think of it. And for each of the different kernels that we were declaring, we had to annotate if the data was only used for input or if it was used for output. And when we do this, then in the compiler level, we can create this task graph, which is aware of the memory, like the explicit memory dependencies between the different tasks, right? So here in this simple toy example, right, I declared 3 tasks and I declared some specific variables, right? You can think of them as being arrays, and they have explicit data dependencies, right? So here, task 2 explicitly requires a specific memory data A that was generated by task 1, and so on and so forth. So then we need to create an energy model that includes multiple things. So first, we need to characterize our kernels, right? And their tools, which allows us to automate these measurements and perform characterizations of our core convolutional kernels. Then we also need even a small linear model for the energy, for the energy consumed by memory is enough. So we need to just know how much energy it takes to write a certain amount of bytes. And then with this, we're able to create the full Julianing model. So Ladybirds is the programming model that the special programming model that I mentioned. So by combining these special programming in the special programming model with this energy model, then we can optimize to given constraints and minimize and know that we have really an optimal solution for the minimum energy that satisfies the constraints for that application. Okay. So it might look a little bit complex, but here I have a very simple example with this simple application of 3 tasks and just some simple data dependencies between the tasks. So here we're dealing with a single core system, right? So we don't tackle things with parallelization, which are known to be NP complete. And so here, the sequence is already given for us. And then from this specification, we can create this state graph, right? So this state graph represents the state of the program before or after executing a particular task. So state 0 is at the very beginning, before you have executed task 1, and state 3 is after you have executed task 3, right? And the edges of this graph represents the tasks that you need to execute to get to the next state, and the data dependencies that you need to be aware of either for saving or for restoring, right? So once we have this graph, and remember we also have an energy model, so characterizations of the individual tasks, as well as the model for the memory. So we know how the T and the D look like in terms of energy. And then we can then simplify the problem by taking the constraints into account, right? So we know that we have a maximum amount of energy storage, right? And this is a variable that we can adjust. And once we do, then we can perhaps prune some of the edges because we know they're too heavy. This was the edge of doing everything at once, right? And just jumping from the state 0 to state 3. So this one, it would be perhaps too high of a Q. And then once we prune it and reduce a bit the space, we can perform Dijkstra's algorithm to find the shortest path between state 0 and state 3. And then in this example, let's say it was this particular path, right? With this solution from Dijkstra, we know a couple of things. We know then the burst schedule, so each activation is called an energy burst. We know from each individual edge what we need to do in that activation. So here it means we need to run task 1 and task 2 together and only save and restore the data dependency B. This is a fairly common result because you could think of it as, for example, if this was the processing of the, so if this was taking the image and this was processing, then this data dependency is very large because it's the raw image, right? Of course, you can extend this to 5,000 samples and you can split the processing over many, many steps. But as the numbers reduce, then it's a good idea to somehow group together the first 2 tasks as much as your energy storage allows. And then the other thing that you can do is you can estimate your actual queue, effective queue that you can select, because it could be that the addition, or let's say the energy of the individual bursts is perhaps significantly smaller than your constraint, right? This depends on the task sizes and on the sizes of the dependencies, right? So it also tells you, hey, you can, for this constraint, you can select an even shorter energy storage task and nothing changes, right? So just to give you a sort of overview of what you can do with Julianing, you can do this design space exploration of trying to minimize the energy cost of your batteryless camera application, right? So here, if we have on the x-axis the energy cost, and on the y-axis this energy storage limit, Q. Here I've placed the 2 default solutions that I had mentioned earlier. So if we have all the tasks executed atomically, the energy cost is small, but the Q is very high. If we do things individually, then the cost is very high, but the Q is very low. So when our energy constraint is quite high, then it's very easy and clear that the optimal solution in terms of energy is to just perform everything together, right? For small applications, this is usually the case and fairly reasonable. But the interesting part is that when joint tasks is a huge energy, I can also select a Qmax that is smaller than this. And this is then where Julianing really shines, because it allows you to select a variable Q. Q has to be bigger than the largest atomic size, so that's the only constraint. And then it's able to find the minimum, which will be somewhere in the middle, right? So here, let me just quickly go through the results from the from this occupancy estimation application that I mentioned. So the whole application was the one where everything is executed together. That's the one. And you can see that the energy storage was really, really high. It was like 2 joules to run this application. With Julianing, the one on top, so we were able to split these 5,000 something tasks into just 18 activations. It correlates roughly to the example that I had shown in the very beginning of the camera taking the picture and processing it over multiple steps throughout an hour. And you can see that the overhead is significantly less than it would have been if we had to execute each task individually, right? Because saving and restoring the state would have added 2 extra joules of energy for your total application. Okay, so that was, yes?
Thanks. So where do the individual tasks and the dependencies come from? Is that something you can extract from the source code basically because it's kind of written in there, or do you need like another file that specifies that? So how do you do that?
So it comes from the program that is written by the developer, right? So the developer has to use this dialect of C, right? It doesn't change that much. It's really the key. The biggest difference is this additional qualifier of the in or out for the parameters that you put in your functions. And just from that, if you write your application like this, then you're able to calculate your state graph.
So from a programmer's point of view, it would be better to have a lot of small individual tasks, so then the program can do the optimization in a more fine-grained way.
Yes.
Okay.
So yeah, you're absolutely correct. However, there's unfortunately, it's not as easy as that, because the processing, as I mentioned in one of the overview slides earlier, processing is not that big of a deal. You can make them really, really small. You can make each task one instruction if you wanted to, right? You are still limited by the rest of the system, and the rest of the system will dictate really the energy constraints, because you have to take a picture, for example, right? You cannot take one pixel and then wait till you have energy and then take the next pixel, right? You would get a nonsense image. So the energy that is needed to perform this atomic operation of taking a picture, this is a lot of energy. And then as long as the granularity of your processing tasks is a little bit less than this, right? A factor of, let's say, 10 of this, that's useful, but having it 1,000th of it, it doesn't make any difference, right?
Okay, yeah, makes sense.
Mm-hmm. Any other questions?
I think my question comes a bit on top of what Sebastian already asked, because the definition of task plays a big role here, how we are going to define it, because this is also a pretty old problem, how we do checkpointing in a program, how we are dividing it into smaller checkpoints. And do you consider the hardware constraint here, for instance, as you mentioned, if we have a camera, it means probably the camera or probably the wireless communication would set the limit, and whatever in between comes is somehow would be smaller in any way. And if so, is there any way to somehow then do the checkpointing according to this energy limit? That we say, okay, let's consider a really worst case that our computation is even larger than communication. Then we set the minimum atomic task, the communication one, and now we adapt the program into this minimum atomic energy required.
So
and
that I agree with you with what you were saying right now, and that is indeed the case that we have here. So I didn't mention it, but this minimum energy storage of 132 millijoules, that is not an arbitrary number. That is the amount of energy that you need to take a picture, a thermal picture, and save the data.
And then on the design exploration, do you also consider the hardware constraint of your storage, the cold start, the maximum capacity, or you consider them fixed and then you adapt everything accordingly?
So I consider, so I consider just the Q, right? And the Q is then your energy limit, right? How much you can store. The cold start, I don't consider separately because it's proportional to this, right? So if you need to store 100 joules, you need a particular capacitance that can store 100 joules. And that capacitance then is tied to a specific cold start. So all I know is that I need to minimize C, so I need to minimize the energy. So the fact that the one thing that is set is the voltage band, right? So to make the last step between the capacitance, right? So the formula 1/2 CEV squared. So the delta V there is the thing that is fixed. Mm-hmm.
And probably an interesting extra future work would be consideration of approximate memory on top of that, because then you can play with the voltage memory, voltage levels.
What do you mean by approximative memory?
For instance, for many NVM technologies, you can reduce the voltage level. Of course, you lose a bit of data accuracy, but you have less voltage level.
So you mean volatile memories?
Yes.
Okay.
No, sorry, non-volatile memory.
But you can have
During the
0
operation,
volts.
yeah, during the operation, when you are reading and writing, you can play with that. Of course, it affects the speed of reading and writing.
Yes.
But you lose a bit of accuracy on that.
So yeah, absolutely. You can totally try to do this.
Because then you add another dimension to this optimization problem.
Yeah.
Then, but you can probably reduce the operational voltage range, and then maybe some interesting task comes in.
Yeah, for sure. I mean, there are other things that you can play around and trying to. I mean, just the memory technology itself is also a big variable that here I didn't take into account. I just had the specific number for the memory, and that's it. Any other questions? All right, so now I will talk a little bit about wireless communications, right? It's sort of like the last step, that if you have your low power sensor that gathers data, performs some processing, we want to get this information out, right? So since I expected that most of you would not be telecom engineers, I'll have just a few slides to maybe refresh a little bit that you might remember seeing in some of your courses. There are many different types of protocols, right, that operate on different bands, have different characteristics. Here, I just put 2. So one being the range. It's a very important parameter, of course. If we have something short range like Bluetooth or something long range like LoRa. Data rate is also another important one, right? So if you have something like Wi-Fi, you know that you could transmit way more data than if you have something like Bluetooth, right? So there are many of these different protocols, but protocols and physical modulation schemes, right? So it's not just higher level things, but it's down even to layer 1, to the physical layer. So when we talk about wireless communication, I just thought it was worth mentioning how the range is actually calculated, or how it actually works, right? It's not really how it's calculated. So when you transmit something, and here this is an example for a LoRa transmitter, you get to have a transmit power. The maximum typical one depends on the range. You can get 14 dBm, right? So this is what comes out of your radio. Then there's some connection losses before it gets to the antenna. Sometimes the antennas might also have some sort of amplification themselves. And then at this point over here, it goes from being in the antenna to being radiated typically as a sphere, right? So it's a cube, sorry, it's a sphere that is decaying quite quickly, the energy that decays quite quickly with space. So the path that it takes can be very variable, right? You have many things in the middle, and at some point, right, if you have a receiver, it reaches an antenna, but the attenuation of the signal is so much, it might have gone to minus 100 dBm, and remember, dBs are a logarithmic scale, so it's many, many orders of magnitude less. But as long as your antenna is able to receive the signal above its sensitivity, and the sensitivity depends on the modulation scheme, if this condition is held, then you can decode your packet, right? Sometimes then you also have some amplification in the antenna, you have some connection loss, and then it gets connected to the radio, right? So in LoRa, you have a very big link budget. Link budget is the difference between the transmit power of your signal and the receiver sensitivity, which again depends on your modulation scheme. So the range, right, depends on many things, but it's tied to the distance here and the path loss that the signal will take, right? So there are many factors that affect this path loss and the fading of the RF signal. One of the key things, just to highlight a difference between different types of communication links, when you have 2 antennas that are, let's say, at the same level, let's say altitude, you have many different Fresnel zones, right? This is something from physics. And to have a good link connection, you should avoid having obstacles between the Fresnel zones. In particular, if you talk to RF people, I'm not an RF person, they say if 60% of the Fresnel zone, or the first Fresnel zone is free of obstacles, the connection is good enough. Right? This is sort of like a rule of thumb, right? So things that can affect it, if you have trees, if you have buildings, you have any type of material that blocks this Fresnel zone, then it increases your path loss, right? So this explains why generally it's a good idea to put one of your antennas in the highest place in a city, so rooftops or a mountain, because it decreases the probability that the Fresnel zone will have obstacles, right? So this means that if you combine these two things, I have put here in this little table different physical layers of different wireless communication technologies, something like Bluetooth, Wi-Fi, something called FSK, frequency shift keying, and LoRa, right? Now here, as I mentioned in the previous two slides, you have a transmit power, which is usually the regulations that say how strong your signal can be. And then here you can see that I've almost ordered them by their receiver sensitivity. So Bluetooth has, which is a short range wireless technology, has a sensitivity of -97 dBm. It gives us a link budget of 92. The long-range communication schemes like LoRa have a link budget of 151, right? And this is what allows LoRa to tolerate, more significant fading of the signal. That is what gives it the extra range, right? So just to give you an idea of how these Fresnel zones work and how they can make a big impact, the theoretical range in free space, so when you don't have any type of obstacles in any of the Fresnel zones, for LoRa is about 850 kilometers using regulations from the US. Now, of course, if you have receivers based on the ground, you will never get to 850 because, as I mentioned before, you have these severely increased path loss, and then your signal decays very rapidly with the distance. But the world record for LoRaWAN transmissions was set a few years ago with a hot air balloon. And so some people in the Netherlands had this LoRa transmitter on a balloon that went up in the sky several hundred kilometers and was transmitting these packets. And there was one station in Eastern Czech Republic that was able to detect the packets that were being sent, right? So here you can see that because it's towards the sky, you have very little attenuation, you get very close to this theoretical range, right? And then when you have lots of obstacles and things, then the practical range decreases significantly. So there's even a more recent experiment that pushed things even further. They used this radio telescope, and with a much higher transmit power of 350 watts, and they blasted this LoRa signal to the moon, and then they switched it from transmission to reception, and then they read the reflection of the LoRa signal from the moon, and they were able to decode the packet. Right? So this signal, LoRa signal, was transmitted over 730,000 kilometers and took several seconds at the speed of light to go back and forth. Right? So this is just to give you an idea of the range that you can get with some of the recent advances in low power communications. Okay, this is not low power, so I meant long range communication schemes. Right? So now if we go back to Earth and we look at how we can use these different technologies for our batteryless sensors, let me give a bit of a summary of how you can build a network with them. So the first one is this asynchronous communication. Asynchronous communication is the thing that I've already mentioned. You have this sporadic activity. You can have your sensor wake up at any moment and you transmit one packet and you go back to sleep. You have a receiver that's always on and it can decode the packet. Things work fine. Okay, they work fine up to a certain point because you have capacity bandwidth limits, right? So this means that if you wanted to transmit more and more information, you have to use some synchronous communication, right? Synchronous communication means that you divide your time slot in particular windows and you have rules about when things can be used. So now in the interest of time, let me just move a little bit. I wanted to talk about a specific protocol called network flooding. And this allows you to have multi-hop networks that can leverage energy efficient short range communication. And they have high reliability and many other interesting things. And it works as follows. You can have a transmitter that sends a packet. It's received by its two neighbors. Its two neighbors, after a very short amount of time, retransmit this data, and it propagates throughout the network like this, right? So this protocol was developed many years ago, and it's been shown that it has very high reliability, and you can transmit efficiently broadcast information throughout the network. Right? Now, to use this type of protocol in the scenario that I was describing before, of having nodes based entirely from energy that is harvested from light, we have one big challenge that we need to solve. And so the question is, if we have two nodes that are in the same room, but one gathers way more energy than the other, how can we actually get the two nodes to communicate efficiently and make most effective use of their energy? So the way we do this is by having two different types of communication rounds, right? So we have to address an issue first before we have a fully functional system, because if we have a topology that looks like this, let's say we have the blue nodes that are low power, so they're not going to be active when the high power nodes are being more active, then we have the issue that when we're trying to communicate between only the high power nodes, there are some disjointed nodes because they would have normally depended on a low power node to relay the information for them. So basically, if we have these low power nodes, they can break our network connectivity, and we need to address this issue. So the way we do this is by playing around with the modulation schemes, increasing the range, right? Such that in this first round over here, we can have these short hops with all types of nodes. And then on the right-hand side, we only have a subset of the nodes, the high power nodes, but they increase their energy costs to communicate with further range and maintain their connectivity, right? So to conclude, right, I've shown you many different possibilities to work with sensors, to perform even complex processing locally on your device. There are many different application domains where they are applicable, right, even though they're not a universal solution for everything. But there are many interesting opportunities in different fields: audiovisual processing, air quality monitoring, wireless communication, as I briefly mentioned. And this is something that I'm looking at not just alone, but with many colleagues, with other professors in other universities. I've also had the privilege to collaborate with industry, with different companies, also large semiconductor companies. And overall, it's been a very long road. You have my email here. You can also visit a website called batteryless.org, where you will see most of these designs, that some of whom I was able to talk to you about today. And yeah, so I will have a demo later on, but I guess we can cut here for the session. I'll show you the rocket logger if you come after the Q&A. Thank you for your time. Are there any other questions?
So any questions?
No questions? Should I show a bit of the demo?
Yeah.
So that, yeah. All right. So for the demo, I have one of these batteryless nodes. This is the first one that I showed that only, so in this particular application, it measures temperature and humidity sensor, and it broadcasts the data via Bluetooth. I have also connected this to one of the rocket loggers. And here I have both the input current as well as the consumption current from the application circuit. And I also have multiple voltage channels that I'll show you in a bit. You can also try this out from your computers, right? So I have a little router here that has a network for the rocket logger. So the first password is Dortmund to join the Wi-Fi network, and then you can go to this IP address and use this username and password. Once you try this out, you will see a website that looks like this. So what I'm looking right now is at the website from the rocket logger server, right? Here I have some control panel where I can change which type of channels I want to record. If I also want to save the data here, I'm not saving the data, I'm just visualizing the data. So the rocket logger shows me the plots separately. So here I have the voltage channels, and then here below I have the current channels. Now I'm just going to enable the input current. Here it's negative polarity, but obviously this is the current that's being harvested. So right now, with this small solar cell and this amount of light, I am harvesting around 60 microamps of current. And I can tell you that voltage V1 here, it's the panel, the voltage of the solar panel. So if you multiply 60, let's round this up to 2 volts. So it's about 120 microwatts of input power right now with this small solar cell with this amount of light, right? Now the red trace is the capacitor voltage. And hopefully this curve is by now familiar to you. So it's charging up slowly until it reaches 5.2 volts roughly. And once it reaches that amount of that voltage, it has reached the maximum amount of energy that it can store. And so at that point, it wakes up, the microcontroller wakes up, and this is what we see here with this current peak of the consumption current. So these peaks here correlate to the voltage going down because it represents that the device woke up and consumed some energy. And so now I can show you some, so you're convinced that it's a real life demo. I can cover with my hand the solar panel, and you can see then that the voltage of the capacitor somehow flattens, right, on the top, right? So the V3. And it's actually, if I cover it completely, it should start to go down a little bit, right? Because the device is on, it's in sleep mode, but it doesn't have any input energy, right? So it will slowly start to discharge. If I leave it like this for a few minutes, it will be completely powered off, right? But as soon as I expose it to light, right, you would see then here, this is the voltage of the solar panel, right? It jumps because it receives more photons, and then it starts to charge up again much more quickly. You'll see that it takes a little bit. There's some things called maximum power point tracking. I didn't go into the details, but basically it has to readjust to the new power point of the solar panel, which depends on the amount of light and the number of cells inside the solar panel. And then right now it has a steady state of around one activation every 2 seconds, right? And yeah, so I mean, obviously, if I were to have here with my handy lamp even more input energy, you will see that the execution rate increases, right? Just because it has more energy, so it charges up faster, and it has more executions, right? So that's the demo. You can see also, I mean, I think I'm cutting into your break time. So if you want, you can go to a break, or you can come down here. I can show you also some receivers. I can talk a little bit more about the card. So yeah, thank you. That was the demo. Are there any questions?
No. Yeah. So since there's no questions, so thank you again for your nice talk. So if you have any questions or you want to try demos, yeah, please. Okay. Yeah.
Okay. Yes?
I recommend that we go see the research hall there.
Oh, great. Where we measure the voltage, and then from this we get the current. So it's a little bit more complicated because we have to do some things called range switching, so that you can have an accurate measurement at low currents and also, okay, low of like nanoamps and high as in milliamps. So those are sort of like the ranges for the rocket motor. But if you are interested in, for example, if you just have to measure something that has a USB port, there are devices that you can buy. They're like USB power loaders. And basically you connect it to USB, and then it has another USB port, and it measures the current that goes into the other USB. So the only, let's say, constraint or difficulty there is that you would be measuring the power of the whole board. And you might not be interested in the total power of the board. You might be interested in a small component of it. And then it's hard. So you might be able to do some differential measurements. So for example, you measure something when the device is off, and then you measure it again when the device is on, and then you subtract. You can somehow say this extra energy is from the device, but it's less exact, so to speak.
One question to your talk. Very good talk, by the way. What is the future plan? So since I'm now currently around a year in the video project, and
Yeah.
like Maya has just always like talk about this the same thing. It sounds really great, but what is the goal then?
So there, I mean, so the thing is, I'm not really involved with the entire project, right? So I can't say.
But it's just every time he says it's really cool and he's really hyped up. But I'm always like, so now it's month after month. It's like, yes, but what is now the plan? So like, I get it. You have the kind of credit card thing, and
well, you can do local processing, right? So the cool thing about it is that so you can do some local processing, and it's like using free energy, so to speak.
So basically, your next step is like the application, or to refine the application, or at least get more applications running on that.
Sure, yeah. But as an academic, that's not, strictly speaking, my main goal.
Yeah.
Right.
Obviously.
So so with my collaborations on the meetup card, there are other interested parties, of course, in an end goal that they can market, they can sell. And then this depends a lot on the specifics of what the customer needs, right?
Yeah.
There could be something as simple as you want to perform, or the customer wants to perform some sort of, what's it called? Preventative maintenance, predictive maintenance, yeah, predictive maintenance. And so with the accelerometer, right, on things that have motors, you can do this, right? You can deploy this low power sensor, record the data if you have the right model, right? Which of course depends on the data set that you gather on your machines, blah, blah, blah. Then you're able to run these types of predictive maintenance algorithms directly on the network. Now, you will of course be a bit limited in the fact that they are not going to be running without light. But if this is not a deal breaker because in factory you have light, and then you're okay with this, then it works and you're good. So there are also some asterisks about the wireless communication, right? In particular because of the range. Right? And so, as I mentioned before, the meter card currently uses Bluetooth. If you have a large factory, this is not going to work.
Yes.
Right? Or you would need to have routers everywhere.
But then I think 5G is the new technology for manufacturing plants, and then
What's right?
5G is the technology for that.
Yeah, but that's too much energy.
Yeah, that's too much energy. That's what
So,
I was thinking.
and it's too expensive too. I mean,
Yeah.
it depends. I mean, industry has
But
money.
usually yes, yeah.
Because I mean, it's bigger. You need the SIM card. You need something that you're using. Typically, some sort of
Good afternoon. Can you hear me? I cannot hear you though, Jane.
Now you should be able to hear me.
Yeah, I can hear you now. Let me plug in the external microphone.
Yes.
Hopefully that would be better in terms of the voice quality. Okay, can you hear me now?
I can hear you perfectly.
Okay, then let me share the slides.
Yep.
Share screen. And maybe I should make it as full screen mode. Okay, seems like it worked.
Yeah, looks good.
All right.
Okay, then one more thing to test. Hang on, to hide this. And move this down here. Okay, I'm muting this computer, and I will move to the other one that is putting you on the speakers here in the lecture hall. Give me a second.
Okay.
Yeah. Okay, can you still hear me?
I can hear you.
Now we can also hear you on the in the hall. Perfect. Okay, now I only have to pin your video. Now we can also see you. Okay, I think it's perfect now.
Wonderful.
Right. So we have 5 more minutes left.
Yeah.
Until we can start. Yeah, okay. That looks good. Yeah, you should also be able to see the lecture hall right behind me.
Yeah.
And so currently the audience is in outside to have a coffee break, but they're coming back in 5 minutes. Hang on. Okay, yeah, thanks for tuning in online. I'm happy that this is working out and that at least we can have you here virtually.
Yeah, nowadays travel takes extra overhead.
Yeah, true.
So I guess and your side, Dortmund in the dinner time now?
Almost, yeah. So it's
Almost.
half past 5, and after your talk, we will move the people over to the conference dinner, which is at 7:30. So, yeah.
Wonderful.
Yeah. Okay, then let me quickly grab coffee or something to drink, and then in 3 minutes we can start. You can actually already talk to Genji. He's one of our PhD students and PhD representatives, and he will do your introduction. Okay?
Sure, sure.
You go.
Yeah, okay. Where's the camera?
I'll put you on the facing camera. That's best. There you go.
Okay, okay. Hello, hello.
Hello.
You can talk. If you want to. There's something to
Yeah. That's for me. Oh, yeah. It's muted. Oh.
I'm muted.
Okay. Okay. Okay, so the next lecture is going to start. So yeah, please go back to your seat and yeah, be quiet. Yeah, so yeah, again, welcome to our resource-aware machine learning summer school. So the following lecture is given by Professor Dr. Liang Chen. Dr. Liang Chen is a professor and chair of the Department of Electronical Engineering and Computer Science at the University of Toledo. He pioneered the research on services computing of mobile and Hawk networked appliances, an early form of the Internet of Things in 2000. While serving as a computer science and engineering faculty at Lehigh University, he was a founding member of the Integrated Networks for Electricity Research Cluster and a leadership council member of the Institute for Cyber-Physical Infrastructure and Energy. So today he will talk about embedded ground designing for pavement monitoring and its incentive mechanisms. So Leon, now the stage is yours.
Thank you very much for the introduction. Good evening, everyone. I'm glad that even though I won't be able to meet you guys in person, but having this opportunity to share the information of a project that I led and worked during my tenure at Lehigh University. By the way, thank you, Dr. Christian Whitfeld, for the invitation. Currently, as the introduction said, I'm a professor and chair of the ECS department and the University of Toledo. And my talk today focuses on embedded crowd sensing for pavement monitoring and its incentive mechanisms, while machine learning techniques have been used and studied. So if we think about the road infrastructure and it increases in size and complexity, the solutions must be developed to cope with road degradations. And the current methods used to collect road conditions information do not mitigate the stress in covering millions of miles of roads. It's just in the US. In the world, there are even much more coverage needed for monitoring the road conditions, especially pavement conditions, because that's critical for the safety of the vehicles and passengers. And measures for road pavement condition monitoring have been developed. Usually it takes advantages of precision instrumentation to realize automatic measurements. For example, people use laser, like a laser crack measurement system, using like high-speed cameras and customized optics and laser line projectors to acquire two-dimensional image or three-dimensional images of the road surfaces. However, these pavement monitoring procedures are time-consuming and costly, which limit their abilities to scale in frequency and coverage of the pavement monitoring. The state-of-the-art research in this domain employs embedded crowd sensing through mobile phones to provide a low-cost approach to pervasive coverage sensing. So in this case, the users of the crowd sensing platform could automatically detect and report poor road conditions by using embedded cameras, accelerometers, and wireless data networks. As you may know, like US Department of Transportation has initiated a connected vehicle program, which promotes applying vehicle to X data to pavement monitoring. A study by the Center for Automotive Research and administrated by Michigan Department of Transportation reports that using V2X data for pavement monitoring is possible, but it will require novel and proactive techniques for data usage and management. So when we consider road surface inspection or monitoring, it is primarily based on visual observation nowadays in the current practice by human beings, like a visual observation by human beings, and combined with quantitative analysis by expensive machines. Considering like the one I show on this slide, you have this kind of vehicle, specialized vehicle with laser crack measurement detection devices mounted on the vehicle. And then people drive the vehicle along the highway, secondary roads to figure out whether there is some degradation of the road surface which need to be repaired or maintained. So considering the scalability issues using the existing approaches, attempts have been made to develop a method for analyzing road properties by using a combination of the recordings by in-vehicle cameras rather than using this kind of expensive devices and a specialized vehicle, but just to use normal vehicles and use either in-vehicle camera or onboard camera, and then use image processing techniques to make the inspection of road surface more efficient and cost effective. And for example, a previous study proposed automatic asphalt pavement crack detection method using image processing techniques and a naive Bayes-based machine learning approach. In recent years, it has become possible to quite accurately analyze the damages to road surfaces using deep neural net. I will talk more about it in later slides. So when we consider the examples of using DNN, deep neural net, for road damage detection, there are examples like CrackNet. It determines the existence of damage from road images. And furthermore, the application of deep learning for road surface damage detection or identification has been proposed by other studies, such as by Zalmans and Akosu's research to identify, say, vertical cracks on the road and horizontal cracks or crocodile cracks. So it's important to note that classification here in this application refers to labeling an image rather than identify object, while detection in our discussion means assigning an image label and identifying the object's coordinates, as show probably you have saw those kind of practice, like a detection versus classification in ImageNet competition. So we basically use similar definition for classification and detection. And in this talk, I will present a recent research that have been used by our pavement crowd sensing platform, which is a DNN application for road damage detection. And it was done by a group in Japan by Mieda and others, where 8 classes of road damages have been studied when applying various deep learning methods for road damage detection. For example, in this categorization of 8 classes of road damages, as shown here on this slide, in the top figure, it shows a class D00 of linear and longitudinal crack in Wehrmacht pots. The rightmost figure on this slide basically shows a class D01 of linear and longitudinal crack in construction joint pot. Then the bottom figure shows both a D00 crack and a D10 crack, which is a linear lateral crack. So it's more like a horizontal kind of crack. And besides the previous classes shown in the previous slide, D0, D01, D10, this slide shows additional 5 classes of road damages. And basically, D11 represent linear lateral crack, and it caused by construction joint. The D20 shows so-called alligator crack, in which you can see that the surface is like the skin of an alligator or crocodile. And then the D40 shows an image of pothole, and that's a normal road damage category. And then D43 shows the crosswalk lines were in blurred condition, which need the maintenance or repainting of the lines. And D44 shows the white line blur. And then the study basically has created a huge data set, I mean, in terms of the application for road damage detection. And the collected images, well, 9,053 images include cracks, were annotated manually with bounding boxes and corresponding labels of road damage class information. Those 8 classes of road damages were used to label the bounding box of in the image while the road damage is shown. The dataset format is designed in a manner similar to the Pascal visual object classes, so that it is easy to apply many existing methods used in the field of image processing and machine learning. So in object detection systems, a conversional feature extractor as a base network is applied to the input image in order to obtain high-level features. The selection of the feature extractor is considerably important because, you know, the number of parameters and layers, the type of layers and other properties directly impact the performance of the detector, right? Or the object detection, the road damage detection. And for example, DocNet 19 is a base model of YOLO. You look on one's framework. The model has 19 convolutional layers and 5 map pooling layers. And VGG16 is a CNN with a total of 16 layers consisting of 13. Yes.
Ian, can you hear me?
Yes.
We had a connection problem. The connection broke down.
Okay.
So we couldn't hear you for about like 2 minutes. So maybe, can you go back?
Sure. So I can go back to the dataset slide.
Is that it? Perfect. Yeah.
Okay, sure. So basically, the data set contains the raw data set collected contains 15,435 damages bounding boxes, and there are 9,053 images include the cracks, and they are annotated manually with bounding boxes and a corresponding label of road damages, like class information were provided. The data set format is designed in a manner, it's kind of similar to that used by other popular projects, which is the Pascal visual object classes, Pascal VOC. In this way, many existing methods in image processing or machine learning could be applied to the set of images in the data set. Yeah. So this slide basically summarizes the best network used for feature extraction and the framework that have been started, like a machine learning framework that have been started for road image or road damage detection. And in the object detection system, convolutional feature extractor usually is used as a base network. And it applies to the input image in order to obtain high-level features. The selection feature are quite important because that would impact the performance of the detector. And if you check the literature, there are quite a number of best networks proposed for feature extraction in image processing when a machine learning approach is used. For example, DocNet 19 is a base model of a YOLO framework, and it has 19 convolutional layers and a max 5 max pooling layers. And VGG16 is also a popular one. Is a CNN with a total of 16 layers, consisting of like 13 convolution layer and 3 fully connected layers, which was proposed in the ImageNet large-scale visual recognition challenge in 2014. And MobileNet, because when we consider a resource-constrained environment, right? So like in the mobile phone app, people need to make the machine learning approach being aware of the resource availability. So MobileNet was proposed, and it shows that it can achieve accuracy comparable to VGG16 ImageNet dataset with only 1/30 of the computational cost and the model size. So which is quite important for mobile app using like DNN for image processing. So basically it is designed for efficient inference in various mobile vision applications. Its building blocks are kind of depth-wise separable convolutions that factorize a standard convolution into depth-wise convolution and a one-by-one convolution, effectively reducing both the computational cost and number of parameters. So the Midas research started the fast RCNN, YOLO, and SSD framework. The fast RCNN has 2 stages. In the first stage, images are like processed using a feature extractor like a VGG16 or MobileNet, and which is called the region proposal network. And simultaneously, some intermediate level layers are used to predict class bounding box proposals. Then in the second stage, this like bounding box proposals are used to crop features from the same intermediate feature map, which are subsequently input to the remainder of the feature extractor in order to predict the class label and its bounding box refinement for each proposal. Basically, fast RCNN inputs the entire image once through a feature extractor, just like the